Let's solve this problem. Remember from our previous discussion, we need to think the optimal solution as a sequence of choices. We also have to set up a recurrence for the optimal cost. Okay, and we call this step 1, characterize the structure of an optimal solution. Okay. Well, let's look at an example. Here we have 6 matrices, and let's use M1, 6 to store the optimal cost for this multiplication. Okay. Then the choice in the optimal solution would be whether the first split happens between matrix A3 and A4, for example. Okay. Of course, in the optimal solution, the answer can be yes, the answer can be no. Okay. Let's say the answer is yes. In an optimal solution, the first split indeed happens between A3 and A4. Then we have 2 smaller subproblems. The multiplication of A1, A2, and A3 is one subproblem, and the multiplication of A4, A5, A6 is another subproblem. So we want to write a recurrence for M from 1 to 6 with the result of 2 smaller subproblems, M13 and M46. Okay. However, there is a very important property in this problem to allow us to set up such recurrence. Okay. So let's first look at what are the possible combinations and why it is important for us to rely on some property to reduce the number of choices. Okay. First of all, A1, A2, A3 has 2 alternative orders. So we can calculate A1, A2 first, or we can calculate A2, A3 first. Similarly, A4, A5, A6 also has 2 alternative orders. The brute force will check the combinations of all these orders, right? So that will give us 4 different orders. Let's calculate the cost. The dimensions for A1 is P0 by P1, and dimensions for A2 is P1 by P2, and dimensions for A3 is P2 by P3. Okay. So the outcome of this first subchain is a matrix of P0 by P3. Okay. And similarly, we know the outcome of the other subchain, and the result is a matrix of P3 by P6. Okay, so the cost for the matrix chain multiplication of A1 to A6, let's say the cost from 1 to 6 is the cost we use to multiply the first 3 matrices and the cost we use to multiply the last 3 matrices, and finally the last multiplication, and the cost is P0 times P3 times P6. So P0 times P3 times P6. Okay, so this is the cost for multiplying the matrix chain from A1 to A6. Interestingly, we are looking for a recurrence for the optimal cost of multiplying matrices from A1 to A6. So when you look at this relationship again, if this is optimal, then these 2 terms must be optimal, which means the optimal order for the entire sequences must contain optimal orders of to subsequences. Okay, you may argue why this must be an optimal value and correspond to an optimal sequence or optimal order. So if it is not an optimal value, it is not an optimal cost, then we can find the actually optimal cost, and that must be smaller than the current one. So we can find a better solution, right? So it's not optimal anymore. Okay? So this basically tells us for this problem, we can set up the recurrence of the optimal cost using the best value we calculated for the smaller problem. Okay? And plus, don't forget the last term, P0 times P3 times P6. This is the fundamental observation of dynamic programming. Okay? This is the fundamental observation of dynamic programming. And this also tells us we don't have to look at all of these 4 different combinations because we only need the optimal solution to the subproblems. Okay? So we just need to check what is this value, and that can give us the value of M16. Okay? So dynamic programming will only check one of them. In other words, instead of all combinations, dynamic programming only checks the combination of optimal solutions to subproblems. And this property has a name. It is called the optimal substructure property. Okay? So an optimal solution to a problem contains optimal solutions to subproblems, as what we discussed over here, right? So we can build an optimal solution to a problem from optimal solutions to subproblems. This is the foundation to build this recursive relationship, and this property can reduce time complexity by safely ignoring non-optimal solutions to subproblems in this recursive relationship. So this optimal substructure property is very important for us to set up the recurrence. And before you can do so, you have to verify whether the problem you are solving actually satisfies this optimal substructure property. And the technique we use is called cut and paste. So basically, we suppose the subproblem solution is not optimal, like what we did over here, and then we try to derive a contradiction. Okay, by cutting out the non-optimal solution and paste in the optimal one, we show we can get a better solution for the original problem, contradicting the fact that you already have an optimal solution to the original problem. Okay? And also be careful, there are some problems that actually does not exhibit optimal substructure property. For example, for this problem, a directed graph, we'll try to look for longest path between 2 vertices. Like for example, the longest path from Q to S is from Q to R, R to T, and T to S. This optimal solution does not contain optimal solution to subproblems. For example, in this optimal solution, the path from Q to R is directly from Q to R, but that is not a longest path from Q to R in this problem setting. Okay, so you have to check for each problem. Use the cut and paste technique to verify it indeed exhibits the optimal substructure property. Okay, and now let's characterize the optimal solution for a general instance. You have to make a choice to split the problem into 2 or more subproblems. In this case, we split the matrix chain. And assume you are given the choice that leads to an optimal solution S. So here, we assume we split the matrix chain between the matrix A sub k and the matrix A sub k plus 1. Given this choice, what are the remaining subproblems? And here, the two remaining sub-problems are sub-chains from A1 to AK and from A plus 1 to AN. And then you have to prove the optimal substructure property by using a cut and paste technique. And here, the optimal substructure property is the order of multiplications of A1 to AK in the optimal solution S must be the optimal order for multiplying these matrices. And similarly, the order of AK plus 1 to AN in the optimal solution S must be an optimal order for multiplying these matrices. Okay? So for example, here is the optimal solution for multiplying 4 matrices, and within the optimal solution, the order for the first 3 matrices is A1, A2 first, and then A3. This order must be optimal for multiplying A1, A2, and A3. Okay. So we're done with step number 1. Step number 2, set up the recurrence. Okay. Let Mij be the minimum number of scalar multiplications needed for compute the matrix multiplication from Ai to Aj. So if we already know where the cut is, we can write something like this. Mij equals Mik, that's the first subchain, and Mk plus 1j, that's the second subchain, plus the cost of the final multiplication. Okay. However, we actually do not know where the optimal cut is, right? So you have to try all possible values for k. And then we have this complete recurrence of Mij. The Mij, when I equals j, Mij equals 0, that means for a single matrix, the cost is 0. You don't have to perform any multiplication. And for a matrix chain that is longer than just one matrix, we have to try all possible k. K goes from I to j minus 1. So basically, you try different values of k, and for each value, we know the recurrence, we know how to calculate the value of Mij given Mik and Mk plus 1j. So we calculate all these candidates and we pick the minimum out of them. Okay? So that's the step number 2.